Well, we're talking now about AC uh, circuits with inductors as well as resistors, and then as well as capacitors. So we're beginning to add the complex numbers to our electrical circuits, and that's what this chapter is about. If you just have a resistor, there's no phase change. If you have 15 volts, 4K, you get 3.75 milliamps. Same it was with DC. Everything is in phase. You might have a little different amplitude, but everything is in phase. But when we introduce an inductor or a capacitor, all of a sudden we get a phase shift. And that phase shift is due to the fact that there is a derivative with respect to, with an inductor, it's with respect to current. With a capacitor, it's with respect to voltage. So you have this phase shift based on the fact that you take the derivative and you get you get the waveform that if you take the derivative the cosine, you get the sine. If you take the derivative of the sine, you get the negative cosine. So it's basically a phase shift issue. And anytime you have an inductor, you have to add this J in front of it. So it's J 2 pi f L. Now the F stands for frequency. So at different frequencies, our reactance, this is called a reactance. It's like the resistance, but it's called reactance, changes. So you have to calculate it for every frequency. You have to calculate it. So if you have an inductor, you have to say, what is my impedance? And it is J 2 pi FL, or J times 2 pi times F, which is 60, times L, which is 0.01, and you get 3.7699. So my current is at a phase shift of minus 90 degrees. Now we can add a resistor into that circuit, and we really have some interesting problems because we have Z, or our total resistance, is 5 plus J0 plus 0 plus J 3.7699 for our resistance. We call it ohms even though it's a complex number. So here we have 6.262, which is 5 plus J 3.7699, which is in polar form 6.262 at angle 37.016. Now we divide V, or 10, by that, and we get I, which is 1.597 at angle minus 37.616 degrees. And we see the phase shift. So you also see that in your labs. When we hooked up the lab, you actually saw that in lab, I think, lab 9, you saw that phase shift. And we can look for voltage, which would be V equals IR, and for resistor, it's I times 5, and for the inductor, voltage is equal to I times the resistance of the inductor, which is 3.769 at angle 90 degrees. So you can see that the voltage is actually shift as well. Here we have parallel, which is 10 volts, and we have the AC sine wave, 60 hertz. Here's our resistor, here's our inductor, and you use the 1 over rule, or you can use the R1, R2 over R1 plus R2. It doesn't really matter. This works, and you come up with an answer, and you get your final value. Now, an aside about this is that when you're traveling through a wire, AC tends to go toward the skin or toward the outside of the wire. As a matter of fact, for low frequencies, 60 hertz or thereabouts, it's not hardly any noticeable effect at all. DC, this goes down the wire in general, but with AC, you can 60 hertz, you devalue the value of the wire by 3%. But at much higher frequencies, the current all travels on the skin or right on the edge. And that's why when you see a high frequency device, you will see hollow metal tubing, which would be the same as that will carry the current through these wires. So that all the current goes down at high frequency, goes down the skin. So you really don't need to provide a solid copper wire. Just provide a tube, and that's all you need. The same kind of formula occurs for capacitance, I equals C dV over dt. And without your phase shift, it goes in the other direction. Instead of the voltage led current in an inductor, current leads voltage in a capacitor by 90 degrees if it's a pure device. So here our phase shift is current is leading. Remember in inductance it was trailing. And our value for the x is minus j over 2 pi fc, or 1 over j 2 pi fc. So for different frequencies, as you go higher in frequency, your reactance or your resistance goes down. It's high, it starts to go down, and it goes down even further here. So now we can look at a value and say what would be our current, and there it is. It's basically, and there should be an angle on this as well, 90 degrees. So current actually leads. But again, we don't just stop with a resistor. We have, or excuse me, with just a capacitor. We have a resistor and a capacitor. And here is for a resistor and a capacitor, my current and the phase shift. And for parallel, the same thing. Okay. Now we're going to start with some problems, and we're going to go through these, and we're going to work some of these out and see what we got. Okay, so we get our sheet here. Okay, so we're now starting with problems at the end of chapter 9, and we're going to go through these and work on them and look at what we got. So let's go to problem 9.1. So we have a value of 6 volts at 2 kilohertz. So we have a capacitor, and so we're going to calculate our value of the capacitor of the x sub c, and that's equal to 1 over j 2 pi f, which is 2000, times the 0.05 times 10 to the minus 6th. So we have 2 times pi times 2 times 0.05, and that's equal to 0.62628, and then times 3 times 10 to the 10 to the third times 10 to the minus 6th, so this would be times 10 to the minus third. So that's j in the denominator, or 1 over that. So x sub c is minus j 1 divided by so it's j 1.591 times 10 to the third, or 1,591, or 1.591 k ohms. So it's equal to j 1.591 k ohms. So what is our voltage and our I'm going to put that up here. And I'm going to erase this stuff so we can now go back and we can do some more work down through here. So now that we found the x sub c, we need to go back and solve our circuit. Okay, so I have 6 volts, and I have 10K, and I have minus J, 1.59K, 1.591K. So what is my current? My current, I, is equal to 6 divided by 10 times 10 to the third plus, minus J 1.591K ohms. So basically, I have to do this now in from rectangular to polar, 10 R to P 1.591 equals 10.125. So the denominator is 10.125 at 9 degrees, at minus 9 degrees. So the current then is I is equal to 6 divided by 10, 125, equals 0.592 at angle 9.04 degrees. So that's our current. And then our voltage is just the multiplication of 10K times this, or minus J 1.591 times this. So that's our answer. So that's how we solve this problem. Okay, moving along to number 2. So for number 2, we have 3K, we have 6K, and then we have 0.02. So here we're really being invited to do a Thevenin of this. So the Thevenin circuit would be 2/3 of 5, or 5 times 2 divided by 3, or 5 times 2 divided by 3, or 3.33. So basically, we're invited to do this. This is 3.33. And then we go over here, and we've got a 2K up here. Now we've got a capacitor. We got to find the impedance of it. So Thevenize when you can, and that's what we're going to do. So all I'm going to do is find that I right there. But I have a 0.02 microfarads, so it's X sub C is 1 over J 2 pi times 1,000 10 to the third times 0.02 times 10 to the minus 6th. So our answer is 2 times pi times 0.02, or 0.1256 times 10 to the minus third in the denominator, and it is the inverse of that, or 7.957 times 10 to the third, or K ohms, and with a minus J in front of it, minus J times that. So I have a I is equal to 3.33 over 2,002K minus J 7.957K, and then my answer will be in milliamps. So it's got to convert the denominator to polar, to R to P 7.957, which is 8.204 at angle 75.89 minus 75.89 degrees. So the answer I is equal to 3.33 divided by 8.204 at angle minus 75.89. So it's 3.33 divided by 8.204 equals 0.4058. Put the answer over here, 0.4058 at angle 75.89 degrees. So that's our final answer. That's our I on that problem, 9.2. Okay, so the next one, find the voltage and current and phasor form for the circuit below. So 9.3. So now we have a problem with voltage. We got to find, okay, so we got to find our X sub L. One is J, 2 pi times F, 10 to the 4th, times L, which is 0.02. Okay, so now we're going to go 2 times pi times 0.02 equals 0.12566 times 10 to the 4th, or 1.2566 times 10 to the 3rd, or 1.256 k ohms. So I have 1.5 k up here, and I have J 1.2566 k over here, and I have 2 volts going in. So what is my I? It's 2 over 1.5 plus J 1.25 1.2566, and that's in k ohms. So I got to do that 1.5 plus J 1.25, 1.5 R to P, 1.2566 equals 1.956. The angle 39.95. So our answer is I is equal to 2 divided by 1.957, or 1.022 at angle minus 39.95 milliamps. That's our answer, and then we multiply that by 1.5k to get our voltage, and multiply that by this to get our voltage across the inductor, and we're all set. 4. So frequency is, for this one, for number 4, 14 volts, 4.5, so 9.4. So we have a 14 volts, and we have 4.5 Henry, big inductor, and we have a resistance over here of 1K, and we have a frequency of 140. So our X sub L is equal to 2 pi, 2 times pi times 140 times 4.5, and that's equal to 3,000. Our X sub L is equal to 33.958 K with a J in front of it. So what is our I? I is equal to 14 over 1K plus J 3.958, and that's in k ohms. So it's 1 R to P 3.958 equals 4.08, and then at an angle 4.082 at angle 75.82. So our I is equal to 14 divided by 4.082, or 3.429, angle minus 75.82 degrees. And then you can multiply that by 4.5, or J 4.5, to get us our voltage across the inductor, and by 1K to get us our voltage across the capacitor, and we're all set. We're done. Okay, number 5. For this one, we're being asked to not necessarily calculate the we're not given the frequency, but we're given the frequency, or we're given the inductance. So we've got 3 volts, and we've got an inductor up here that's got a J of J 2K, and we've got a resistor down here that's at 5K, and we've got a capacitor over here that's at minus J 2.5. And sometimes this is the way it's given to you, and that's okay. But now what do you have to do with this? Well, you first have to, they ask for the I across this right here. So I have to combine these two, and I have to do it with the parallel rule. So it's 5 times minus J 2.5 all over 5 plus J, 5 minus J 2.5. Now that's what you have to do, and you combine these two, and then you find the I through the whole thing, and we're going to do that. 5 times 2.5 is equal to 12.5, so it's minus J 12.5 over, and this is in K, over 5 R to P 2.5 with a minus sign in front of it, okay? So it's 5.59 at angle minus 26.56 degrees. So I've got my magnitude and my angle, I've got my magnitude, and it's at minus 90, so basically I can use the minus J as minus 90. So it's 12.5 divided by 5.59, or 2.236 2.236 over, not over, but it's at angle minus 90, which is the minus J, plus 26.56. So it is 90 with a minus sign on it, plus 26.56 degrees, or minus 63.44. So it's 2.236 at minus 63.44 degrees, and that is in K ohms. Now that's my resistance of these two. So my current is now based on the value of, and these are going to get added, so it's going to be I is equal to 3 divided by J2K plus 2.236K at angle minus 63.44. And now you have to get this in polar and then divide, and you can do that, and it'll come out. So let's do that. So I have to convert the 2.236 to rectangular and add them. P to R, 63.44, the minus sign in front of it, equals, okay, so the conversion process gives me 1.00 at angle minus 2. Maybe I got that wrong. Okay, let's try it again. 2.236 P to R, 63.44 with a minus sign in front of it, equals again. 2.236 P to R 63.44 with a minus sign in front of it equals, I got 0.99 at angle. Okay, so there's no angle here. It's just 0.999, or I rounded it to 1. Okay, and the minus 2 minus J 2.00. So now I have J 2,000 minus J 2,000. So basically they drop out. And here I have just 3 over 1K, or 3 milliamps. And that's all you have to do there. So that's an easy one. This 2K and this 2K drop out. They balance each other out, and they're basically, they go away. So that's an easy one, but they're not always that easy. Okay. Number 6. That, by the way, is at resonance, where they do exactly cancel each other out. So we're going to do number 6. And 9.6. And find the voltage and current and phasor form for the circuit below. So this one is 5 volts and 10K and 2.5 Henry. And we give a frequency of 100, 500, and 1K. And so find the voltage and current at each of these. So basically this one is going to be recalculating the X sub L 3 times. And I'm not going to do that for you, but it's basically, we've done it for one. You can just do it for each of these frequencies, and you're going to see as you go higher in frequency that this gets to be a bigger number and your I goes down. So that's all that we do with that one. And number 7, it gives the value of X sub L and X sub C, and you basically do the same kind of action that you would with the prior one. But in this case, what I would do on 9.7 is I would, on 9.7, I would Thevenize the 6K up here, and the X sub C, which is minus J 3.5K. I would Thevenize that, and the way you Thevenize that is you find the voltage across and the resistance, and then you can go back and you can find the current through the L much easier. So that would be my suggestion. Thevenize this part, and then from there go ahead and reconstruct it with a voltage, and this voltage will have a phase. It will be a voltage at an angle, and then with a complex resistance, but then you stick the L back in and you can find the I very easily. So again, voltage at an angle and a complex resistance up here, and then find the I, and you're done. That would be my suggestion of how to find this one. That's probably the easiest way of finding the answer on this one as well. So we will stop now and let you think about that one, and we'll pick back up with the latter part of this chapter. So we're going to start again on chapter 9, and I want to review 9.5, 9.6, 9.7, and go ahead and finish the rest of the chapter. So we're going to start with 9.5. And the problem here is we've got a voltage supply at 3 volts. We've got an inductor up here at J 2K, and we have a 5K resistor, and we have a capacitor that has a reactance of minus J 2.5K. So we're going to use, and we want to know the current up here. So we're going to combine these two, and we're going to do that with using the parallel rule, the R1 R2 over R1 times R2. So it's 5 times minus J 2.5 over 5K minus J 2.5. And then the answer is going to be in K ohms. So we're going to not worry about the K's. We're just going to say the answer is in K ohms. So 5 times 2.5, 5 times 2.5, that's 12.5. So minus J 12.5 over 5 minus 2.5. So it's 5 R to P 2.5 with a minus sign in front of it equals 5.59. That's an angle minus 26.56. So we have a 12.5 at minus 90. That minus J is at minus 90 over 5.59 at minus 26.59. So we're saying the total resistance here is 12.5 divided by 5.59 or 2.23 or 2.24 K at angle minus 90 plus 26.56 or minus 63.44. So we've got 2.24 at minus 63.24. Now, what is our I? So our I up here is, it would be like it was going through here and then down through here. So it would just be, this would be my combined resistance. So now we're in series. So basically I is equal to 3 over J 2K plus 2.24 at angle minus 63.44 degrees. Okay, so we've got this, which is imaginary, and we've got this, which is a combined. So we've got to go 2.24. We've got to convert this part to rectangular. 63.44 with a minus sign in front of it equals, okay, this is 3 over, equal to 3 over 1 minus J2 plus J2. So basically this is going to be equal to 3 milliamps. So this is the same answer we got before, but I just want to go through it again and make sure that you got this idea of combining these two. Now the next question, or next problem we're going to do, we're going to look at it, and we're going to do it a little differently, and that is, well, not the next one, but the 9-7 we're going to do a little differently, because that's asking to be Thevenized. So the one is not asking to be Thevenized, and the second one is. So we're going to work through this next one. 9-6, and it is 5 volts, and then we have 10K up here, and then we have a frequency of 100. Let's just do it with 100. So it is J 2 pi times 100 times 2.5, and that gives us our resistance, or Z. So it's 2 times pi times 100 times 2.5, or so again, 2 times pi equals times 100 equals times 2.5 equals 1,570. So basically this is 10K up here plus J 1,000, 1.57K. So we're going to say, what is the current through that? So basically it's going to be 5. I is equal to 5 over 10,000, 10 plus J 1.5 7. The answer is going to be in milliamps. So I got to do the conversion of the 10 plus J 1.57. So I say 10 R to P 1.57 equals 10.12. So it's equal to 5 over 10.12 at angle 8.92 degrees. So when we do the 5 divided by 10.12, we get 0.494 at angle minus 8.92 degrees. Okay, so there's our answer, and that's in milliamps. Okay, so now number 7. Number 7 is, we said we're going to Thevenize this one, which is what we're going to do. So we're going to go up to this point right here. We're going to say, okay, so we got 6, and we got 6K up here, and we're going to find the resistance of this, and then we're going to Thevenize to that point. So we have to say minus J 3.5, and this is 6. So now we're going to find the voltage across that. So the voltage across the outputs, or VAB, which is going to be our VThevenin, is minus J 3.5 over 6 plus, 6 minus J 3.5 times 6. So there's a minus sign there. So it's minus J 3.5 is equal to it's equal to 3.5 at angle minus 90 degrees. And the 6 minus J 3.5 going to 6 R to P 3.5 with a minus sign in front of it equals, so it's the magnitude here is 6.94 at angle minus 30.25. So now we have that whole thing times 6. So I have 6 times 3.5 divided by 6.94 equals 3.02. So we got a value of 3.02 at an angle minus 90 plus 30.25 or minus 59.75 degrees. So that's going to be our VThevenin, 3.02 at angle minus 59.75 degrees. Now what is our R-Thevenin? It's going to be this times this over this plus this. So it's going to be 6 times J 3.5 over 6 minus J, there's a minus sign in there, 6 minus J 3.5, and the answer is going to be in K ohms. Okay, so it's 6 times the minus J 3.5, 6 times 3.5 equals 21. So it's 6 times 3.5 equals 21. 21 at angle minus 90 over 6 minus J 3.5. So we're going to go 6 R to P 3.5 minus equals 6.94 at minus 30. So I have my resistance, my R-Thevenin, is 21 divided by 6.94 or 3.02, which comes up to the same exact number as the other one. So basically we're mimicking ourselves, so it's going to be 3. Okay, it's going to be 6, it's going to be 21 divided by 6.94 or 3.02. It's kind of strange, but we are getting the exact same value for our R-Thevenin, which is 3.02 at angle, notice this, minus 59.25. Now that's strange, but it's just an accident. That's just the way it happens. So we've got the same value for our Thevenin. We've got the same value for both of them because it just the way it happened. But it is what it is. So basically, but it's because this is a 6 and this was a 6. If this would have been different numbers, that wouldn't have worked out this way, but it did. So now we're going to erase this part of it over here, because now we've got our Thevenin equivalent circuit, and we're going to go back now and we're going to put the L back in. So now we've got our circuit with our Thevenin equivalents in here, and we're just going to go back and we're going to try to work through and see if we can do the same thing with our okay, so now we have our Thevenin equivalent circuit and we add our L back in. Say, can you do this? Yes, you can. So this is J4K. This is a K here as well. Okay, so now we have 3.02 at minus 59 and J4K, and we've got 3.02. So we're asking what is the I? I is equal to 3.02 at angle minus 59.75 over this whole thing, which is 3.02 at angle minus 59.75 plus J4K. And this is in K as well. So this is, say, J4. Okay. So we've got this to J4. So now we've got to move this to rectangular and then back to polar to get the final answer. So 3.02 at P to R, 59.75 with a minus sign in front of it equals. So this denominator is 1.52. That's the real part. Minus J 2.60, and then plus J4, so 4 minus 2.6 equals 1.4. So our denominator is 1.52 plus J 1.4, and then our final answer is going to be milliamps. So basically, got a R to P this, so 1.52 okay, 1.52 1.4 equals 2.0. So the answer here is in polar is 2.06 at angle 42.64. So that's our denominator, and this is our numerator. So let's go up here and finish it off. So now we're going to come up here and finish this off. Okay, so we've got our I is equal to 3.02 at minus 59.75 over 2.06 at angle 42.6. So this is going to go up there. So the answer is 3.02 divided by 2.06. 3.02 divided by 2.06, or it's about 1.46. At what angle? So it's minus 59.75 with a minus sign, minus 42.6, or minus 102. So the answer is minus 102.35 degrees. So this is one that goes way out. It goes 1.46 at minus 102.35 degrees. So that's our answer. That's our final answer right here. That's our I. Okay, enough. So we're going to go back and we're going to look at some of the rest of this chapter, and we're going to work on some of the items there. So let's go back and see what we can do here. Okay, so now we're talking about AC power, and so these are basically equations that we just need to tuck away and remember, and if you ever want to use them, you can. And the problems that we're going to do at the end of this chapter here are very simple because they just take these and use them. So 1 horsepower, English horsepower, is 745.7 watts, or 0.746 kilowatts. And so how do you get this P in watts? Well, for a three-phase power, you get the real part, which is square root of 3 times V peak to peak times I peak of I phase to phase, excuse me, not peak to peak, but phase to phase, times the current of any one phase times cosine of the angle, which is the angle between voltage and current. Okay, so here is our formula for brake horsepower. It's the square root of 3 times V phase to phase times I phase times cosine of theta divided by 746. So that gives you the brake horsepower. And here's the angle. If I have phase to phase of 208, what is my phase to ground? It's 120. And you can look at it like that, and you can say, okay, you can understand how people can get 120 out of 208 because of this phasor diagram. This is a phasor diagram showing the three phases of 120, and the 208 is the value between phase to phase. Phase to ground is 120, phase to phase is 208. So if you have single phase, this is what you would say the P real is V times I times cosine theta, or this angle right here, and P var, or the imaginary power, is this right here, and the P total is this right here. And this is what you pay for. This is what you actually pay for in your house. This is what you get out of it. In the house, you don't care too much about losing a little bit, but in industry, when you get this big right here, you're losing quite a lot, and people want to not lose that any more than possible. That's why they put capacitors in factories around motors to bring this number on this vertical line down. So P real is the square root of 3 times the V times I times cosine theta. So I will give you this, I'll ask you for P real or something like that. So basically here, if I give you the values, find these. So here's the voltage is 150, current is 10, phase angle is 35. Find P total, P real, and P var. So that would be this set of formulas right here. Okay. So then for a three-phase, I give you 460, 15 amps, phase angle, find P real, find P brake horsepower for the circuit. Again, it's just using the formulas. And here's another one using the formulas, and here's another one just using the formulas. That's all you have to do for these, is just plug these numbers in, and you'll get the answers. Okay. So here we're talking about motor starters, and how do you start a motor? You close a contactor in front of it, and then the power flows down to the motor, and that's how you do it. There is a thing called an overload that is reading the current to the motor, and if it goes too high over a long period of time, it will tell another circuit, your circuit, the overload contactor, to turn the motor off, and it will turn these off right here. And that's how you turn off a motor with the overloads. Okay. So this is a set of drawings or sequence of various pictures that give you a little bit of an idea about how motor starters work and how you can protect your motor against catastrophic failure and how you can get them started. So this is how you would reverse a motor. You would flip any two leads. And you notice this lead comes down here and flips. You go from 1 to 2 with this contactor. You go from 2 to 1 with this contactor, and 3 stays alone. So basically, anytime you turn any two around, flip 2 to 3, 3 to 2, or whatever, you've reversed the phase of a three-phase motor. Flip any two leads, and you reverse the leads. You reverse the motor direction. Okay, so here would be a simple circuit for starting a motor in the forward direction and starting it in the reverse direction. Push button starts in the forward, push button starts in the reverse. And you notice there's an interlock here that says if you're in the other direction, you can't do the other one. So that would give you a electrical way of making sure that you can't start both in the same direction at the same time, because that would be catastrophic. So here's another one. This is a seal circuit. So you can either start in the forward direction or start in the reverse direction with a simple push button. The stop push button would stop in either direction. So here are some examples of selector switches that would give you the ability to go between modes. There's some ideas of how to hook a circuit up so that you can actually be in auto or manual and do something in auto and do something in manual, and away you go. So this is pictorially what the various parts of the motor starter are. Your motor coil is right here in the middle. Your auxiliary contacts are over on the side. Your overload contact is down here on the overload block, but it's kind of off to the side. And you can see all these various parts. So here's the power leads coming in. Here's your contactor. Here's the two wires for the coil that turns the motor coil on, or the motor contactor on. Here's your auxiliary contacts. And down here is where you have your overloads. And here's your overload. Right here's your overload contactor. And here's your motor leads. These are the leads that go to your motor. So the power flows from the top to bottom, comes out here, and it goes to your motor. Here's some pictorials of the various parts laid out. Here you can see the coil, or where you can see, here's the coil. You can see where the coil fits right in here. Here's the auxiliary contactor. Okay. And here is energizing the coil manually. In other words, energizing the contactor manually. You can actually see this. If you push this up, it goes up, and then the contacts close. We do want to talk a little bit about National Electric Code. Not that we've got to do a lot with the National Electric Code in this course, but at least you should know that it exists. And if you were to ever wonder about how wire sizes became standardized for certain applications, you could look at the National Electric Code and they would tell you the ohms per foot of various gauges of wire, and they list them. So if you have a circuit that, let's say you want to go 100 feet and you can't drop more than a certain number of volts, then you could actually calculate out the ohms per feet, and then you could say, okay, if I go this many feet, the voltage will drop this amount, and if that's too much, then you have to go to a larger size wire, and that's been done. That's something that's done quite a lot. People have what we call rule of thumb, where they would actually say, okay, if you go more than, for instance, 200 feet out for a solenoid, typically you would have to go from a size 14 to a size 12 AWG wire in order to make sure that the solenoid would turn on and pull in appropriately. So again, that's just a rule of thumb, but it's a good one, and you can use those kind of rules of thumb to help you, or you can actually do the calculations and see if it's going to be see if it's going to suffice. So whether or not you use the rule of thumb or you go back to the National Electric Code, either way usually will work. But if you have problems, some of these will be answered by looking through the National Electric Code to find the appropriate answer for a specific question you might have. So again, it's useful. You should have a copy of it if you work in an industry, and you should at least once in your life sit down and look through it. Maybe not read it all the way through, but just know where things are at. And so as people start asking you questions about it, you can refer to it, and you can say, well, this is what this area is concerned with. So again, National Electric Code, latest edition. Recommend you have a copy when you get out in the industry. Take care and have a good day.